In this lecture, what I'd like to do is to rewrite the Lorentz force from its current form, which is the force is equal to the electric charge, Q, times the electric field plus the velocity crossed into the magnetic field. What I'd like to do is rewrite that in terms of potentials. So if you remember from Newton's second law that this force is equal to a change in the momentum with respect to time. So not only if we rewrite these fields in terms of potentials, we may also be able to extract a form for the momentum. Okay, so let's put in now what we know about the fields. So the electric field is minus the gradient of the electric potential minus the time derivative of the magnetic potential plus V crossed into the curl of the magnetic potential, like so. Okay. For the momentum, we're just going to assume it's non-relativistic. So P is equal to the mass times the velocity. Okay, so let's not worry about relativity just yet. Okay, so let's go back, see if we can clean up that cross product term. And so I do know my vector identity, which is the gradient of the dot product of these two vectors is equal to the cross product of the curl plus the dot product of V with del times the vector A. Okay, so now I've got something I can rewrite this. So that means that V crossed curl of A is now equal to the gradient of V dot A minus V dotted into the del times A. Okay. Okay, so let's put that in. And so what we get for the force is Q times minus del V minus dA dt plus the rest of the stuff like so. And what we have is, let's pull all of the gradient stuff together. And so what we have is Q minus dA dt minus V dot del times A. And then, let's see, minus the gradient of V minus V dot A. Okay, I think that's it. So now you notice there's a minus sign. I can pull that minus sign out front, and I get minus Q dA dt plus V dot del times A plus the gradient of V minus velocity dotted into A. Okay. Okay. So now let's consider the differential of A. So dA is equal to A R plus VT, V dt, T plus dt. So we're just shifting everything by a time dt. So the position is shifted by the velocity times the time. The time is just shifted by dt minus A, R, and T. Okay. Now, I can rewrite this in terms of partials. as dA dx Vx dt plus dA dy Vy dt plus dA dz Vz dt plus dA dt dt. Okay, because essentially Vx dt is just dx, Vy dt is just dy, etc., etc. Okay, so that means I can now rewrite the derivative of A with respect to time as dA dt plus dA dx Vx plus dA dy Vy plus dA dz Vz. Okay, which means I can now write this full derivative dA dt as the partial derivative with respect to time plus V dotted into del times A. So this is called a convective derivative, or like so. So basically, I have the force, the time derivative of the momentum, plus the time derivative of A. So what I get is the time derivative of P plus Q times A is equal to minus del QV minus Q, the velocity dotted into A, like so. And so what I get is a force, and now I get a minus the gradient of the potential energy. So what I have is essentially a force on the left-hand side is equal to the gradient of the potential energy, which means I now have this, what you might call a canonical momentum of P plus Q times A, and a velocity-dependent potential energy of QV minus V dotted into this potential, or the electric potential minus the velocity dotted into A. So what that means is that the V, the electric potential, is potential energy per charge, and A is potential momentum per charge. So we now have kind of rewritten this such that we've combined momentum and potential energy with our fields V and A.